So hello everyone. I think everything is good. We have excellent connection, so we can probably start the stream. Okay. It's 7 p.m. where I live, and yeah. Okay. So I was looking at this this trick here, Kruskal Reconstruction tree, and it caught my eye because it is a structure that I wouldn't know how to solve problems if such problem popped up, because it's not easy to see some things, but yet it is very powerful data structure, I would say. I mean, not data structure, it's like representation, moreover, right? So I would love to code it from scratch and see where mistakes are made, and possibly solve this problem. So we're going to try to solve this problem, this division 2 E problem, on this kind of way. So I mean, here first we need to say what this structure is and how it relates to these problems. So the structure is actually like, if you are given some tree and you want to find the maximum edge between two nodes, of course you can use heavy light decomposition and answer these queries in logarithmic time with, I mean, log squared time with heavy light decomposition, because you would have like a segment tree. With binary lifting, that's probably like, yeah, but binary lifting doesn't allow for modification of the edges. This kind of tree here, Kruskal's Reconstruction tree, also doesn't allow modification of the edges as far as I know. Yeah, so it won't allow modification of the edges because it will change the whole structure, unless you have some kind of special rotational things done. But I mean, this is not really the point of this reconstruction tree. It's more the point of like having this ability so that like the maximum edge between any two vertices is represented by the LCA of these two vertices by a node. So here from 3 to 6, this is an edge here, and the maximum edge between 3 to 6 is represented by a node here that joins them together. So if you have this tree, you could technically find like the LCA, for example, from 3 to 2 here. The LCA is 1, 3. So this edge 1, 3 is the maximum edge from node 3 to node 2. Okay, if that makes sense. So this kind of data structure, I think it's really easily built, but the LCA queries are not so easy. We are going to try to build it from scratch, and yeah, so yeah, let's try to solve this problem, maybe. Yeah. So in this problem, they say we are given some undirected graph, and we have to answer queries of the form L to R, where we find the smallest k integer, such that edges from 1 to k are sufficient for the vertices L to R to be connected. So this is such a problem I wouldn't know how to solve if it just popped up, right? But now every edge from 1 to k is like can be thought of as having an index from 1 to k. And now we want to find from the what we want to do is to find from if I want to connect them all of these, like a minimum spanning tree that connects all of these, if you can imagine that, not a minimum, but all of these L to R will be like terminals of this minimum spanning tree, or like inside the spanning tree. Then what is the maximum of these edges here? And what is the maximum value, right? Because each edge we said has value from 1 to k. So I will just go here to this problem and just take it down. So I have some number of test cases. Let me just close this. Oops. Okay. I mean, I don't know if this is quite hard theory here, for quite hard graph theory, but I would want to solve it because I don't have anything like this solved. Okay, so we have some test cases, right? And maybe I will just for this, should I build a data structure that can handle these things? Should I build a Kruskal reconstruction tree data structure? So why not? So build a data structure, and let me see what we need to read here. We need to read M. M is what? Edges. What, aren't they all connected? Oh, so apparently it's a graph. Okay. Yeah, so I thought it's a tree. Yeah, but it's the same holds. So we built an Q. Okay. And for each of these edges, I will join them with a DSU, right? But now the idea is, okay, if I have n minus, so I don't really care about, yeah, the k will be at most n minus 1 edges, because I can join them. Actually, no. Actually, I can have an edge that is redundant in the graph, and then you would have a bigger k. Yeah, that's correct. Actually, k is not bounded by n minus 1. Okay, so a DSU will have parents. And then I will set up all these parents to be themselves, right? Find set will if parent of A is A, then return A. Return parent. Instead of parents, I'll just parent, call it parent. Here, parent of A is equal to find set of A. And then I need to merge A and B such that here A is like A is a child. So if A is a child, I still need to find set A and find set B if like I return, I don't merge them, and then if it's not, I would say the parent of A is B and merge them. So we have path compression with this child thing merge here, which should give us lock and amortized on the DSU. And now the trick here is about getting these reachability things here. Okay. So our first step would be to build the tree, to build this Kruskal's reconstruction tree. Okay, let's do this. We are going to take each edge, so maybe we won't have like a data structure here separate. I don't know, we'll see. Really, I don't know how to cleanly implement this, but okay, so we take for each edge, we have some U and V, right? And then we take this U and V and we say that we have to join them, so the DSU will have more things to. So the DSU is actually like n plus. For each of these, I will have like for each there are n minus 1 edges, so there's like 2 times n minus 1 edges in the DSU. And then each edge will be like n plus I, right? So this will be this edge from U to V, right? And this DSU will, okay, this edge will connect components. This edge will connect the 3 and the 6, right? Yeah. So let me just excuse me for one moment, please. Okay, so this edge here is going to connect these two, right? Yeah. So DSU dot merge U with this edge and DSU dot merge V with this edge. And here what we will do is if I successfully merge them, merge both of these edges, I will actually always successfully merge them, right? Is that correct? So when I will merge well, if they're in the same component, but I could have like another DSU that merges these edges separate, right? How is this best done? If we build the KRT, then the answer is the query. Okay, we know what's the answer, but the key property, the maximum edge between U and V, is their LCA. It's well known how to compute LCA, so successful. What's the code here? The code is just union find, which doesn't help much. Oh, he's actually doing it inside the union find. Okay, I see. So we find this and this, and then if I do this, I immediately have parent of U, parent of V is parent of ID. Okay. ID is the next unused ID. But the next unused ID will be like N. Yeah, N from N and so forth. And then U adjacency of I of this ID is U and V. Is that correct? Yeah, that's correct. So let's do this here. So yeah, we have like some easy DSU, right? And we want to have an adjacency list here. And we want to have and some like ID. Okay, and then we merge, we add an edge. Add edge is like from U and V. With some cost, right? The cost will be I actually, and then I will do the following. I will try to merge. So if merge here U and V. So if merge U and V. Oh, here I'll have a DSU, of course. DSU. DSU with N nodes. Okay, and then I will merge u and v, and if it's successful, if it is successful, then I need adjacency at u dot pushback. No, adjacency at id dot push is essentially u and v, right? That's the adjacency at id. Adjacency resize. Oh, and furthermore, adjacency is like 2 times n minus 1, and the DSU is also 2 times n minus 1. Okay, and we set the adjacency of this. Oh, also, yeah. I should not do this with a proper DSU. I should do it inside here. Because otherwise I need to merge both of these to the component, which would technically be okay. Yeah, would technically be okay, but it's better maybe to just do as he done it. Because if I can't merge them, like if I say that okay, I'm merging it with ID right now, right? Is that the same idea? Well, no, because we will merge them sometimes and lose an ID in the process. Yeah, so actually it's way better to just like compute this here. Instead of having like a DSU, we'll have parents here. Vector of int parent. Instead of doing this, we'll say parent resize 2 times n minus 1, right? And find set also here is fine. Having it here. Now we won't need DSU, but we'll just, okay, find set works the same way. U and V work the same way here. Okay, let's return boolean for just maybe it would be needed. So parent of u is equal to parent of v is equal to parent of the ID is equal to ID. Then I need ID++, and then I return that I have actually merged them. So I find u and v and I say, okay, if they're the same, I don't do anything. If they're not, I'm just gonna merge them. And here the cost here is actually like, if I have a cost here, I should have another vector with cost here. And this vector with cost should be resized to this. And now I can say cost at ID is equal to like ID or something for this problem would suffice. Oh yeah, cost is like C maybe here. Cost is C here. Yeah. I mean, no, not ID. The cost will be what kind of edge I'm adding here. That will be the cost. So okay, so we have the find set and we have the merge function. Now here I will say Carte tree, and I will create the tree, and then the edges are going to like, okay, let's call this add edge instead of, so add edge from U to V, and the cost is I plus 1, because I is the index of that edge, plus 1 will give us the proper cost. So we add like this edge to the tree, and this is exactly what this code actually does here. But now that we have this tree kind of merged up together, we have to run DFS through the tree and find an Euler Tor. Yeah, right? Do you need an Euler Tor for this problem? Yes, I think you need an Euler Tor for this problem. Yeah, because the LCA from all of these vertices from L to R is like, I will have like a minimum and maximum, like a segment tree or a table or a sparse table, and then what will happen is that like I find the minimum and the maximum in this sparse table for the Euler's Tor times, the largest and the smallest and largest DFS times. And then when I find these smallest and largest DFS times, on these times I will just do the LCA, and this will give me the answer. And I won't actually do an LCA in like O of 1 time, because doing an LCA in O of 1 requires like really huge pre-computations, which I won't bother doing it, just because I want to keep this as simple as possible, even though this is nowhere near simple. But let's try to do it as simple as possible, no? Okay, so we have this tree here that we are doing. Now I need like a DFS here, and first, like, the DFS will be like, I'm at some node U, right? I'm descending. I will get the tree here. I will get a reference to that tree, because I don't want it to. Actually, I could do it inside the KRT as well here. Like, I will have DFS1, like DFS times, let's say, and here I could actually just create an array, and this would be time, and this would be time resize 2 times n minus 1. Yeah, that is fine. Now I will need some timer here, starting from 0, and I will say time at U is timer plus plus. So I will set the timer at U, right? And then I will go somewhere down the U path, and then I will return back and I will set the ending timer. So do I care about the ending timer of U, really? Do I care about it? I don't think I care about it, right? No, I don't think I care. Time at U, okay. And then for V in adjacency at U, I will say DFS time V. Now this, because we are not actually, yeah, here we need adjacency at ID is actually U and V, right? Okay. Now I have to start up the tree.dfs times has to start at the root, but the root is the last ID possible which is merged. Okay, so it's the last possible ID, so it's tree.id minus 1. And I want just to print the time here to see if that actually works. Okay, let's just print it. Yeah, I'm not reading the queries though, am I? Okay, let's read the queries. So the queries are what actually here? So we have NQ, then there are edges, and then this is guaranteed. And then there are queries with LNR. Okay, with LNR. Okay, so this should work if I have it all properly constructed. Yeah, so the parent, after the parent I still need this. Okay, so it says that first we have 1 and 2, and then we have, what is this now here? No, this is one edge here, right? So 1 and 2, there's one edge between 1 and 2, so we go this node first, then we go 1 node, then we go 2 node 2. Which is correct, this is correct. Okay, but why does it crash on the next case? What is the idea here? Okay, let's just not run DFS times to see if that's the problem. No, that does not seem the problem. Okay, what is parent of u, parent of v, parent of id is id, and id plus id should be n by default, because there's 0 through n minus 1 are the nodes. Then it starts n, and then there is like, okay, I don't see why is the problem here. What is NMQ, then there is a tree, then we read the edges. If I don't do this, what? Okay, so something is with the adding of edge. Find set is A, then we return A, otherwise is find set of the parent of A. Of course, this is so parent of A set of the parent of A. Parent cost at ID cost, then we have cost, we have adjacency at ID is UV. I mean, this is okay. I think this is okay. I don't know what. 9. What is 9? Okay, 9 is not good. Wait, there are n nodes and n-1 edges. Why are we? It's 5, 6, 7. 0, 1, 0, 2, 1, 3. Okay, that's fine. 2, 3. Wait, what? No. 2, 3 is not fine at all because 2 is already connected to 2 and 0 and 1, 0 and 2, right? But yeah, this is not. Wait, did he have like that? Parent of U, parent of V, parent of ID. Wait, is that correct? No. Parent of U is actually, yeah. This is actually, we override this. So like x and epsilon here is actually what we want here. We want to override this because now the parent node is what we are merging. Yeah, now that should work. Okay, that's a node that I'm supposed to somehow, okay, say that. So node when merging, don't forget to merge parent of x instead of parent of y. Okay. We merged that. We made this Euler tour here, and now for the problem itself, we want. So from L to R, we have some vertices, right? From L to R, and in these from L to R, in a range from L to R, we need to find the minimum and the maximum, which can be done with segment tree or with RMQ. Let's do it with. Well, we should do it. Should we do it with an RMQ? Just to practice the RMQ here. I mean, the RMQ is. I don't know. Should I do it with an RMQ? Symmetry is that easy. Okay, however we do it, when we find the smallest and largest DFS times, it means that we need actually to not find the smallest and largest DFS times, we need to find them we need to find to what indices they represent, right? We need a reverse kind of set. Okay, yeah, let's do it with an RMQ, shall we? With a sparse table. So let's okay, can we template can I do a template here on the sparse table? I'm sure, yeah. I just don't know how it was like the template there. Like you could do a, or what I can do is I copy here a sparse table. What I could do is have a std function here. So I could have like a function that would give me like an integer, and I would have like two integers, and this function will actually mean I could template I don't know, make the template here as well. Like I could do this. Okay. So of course this is a little bit, because it's jump case size j++. This is okay. And now instead here at the minimum I can call the function of these two, and here instead of this I can call the function of these two. Okay, this sounds okay. This sounds okay. Here as well. And now, because we have this function, I need also to set this function to something. So let's just say that I will receive such a function if, and then I will say this here. And now I can create an RMQ on top of the DFS times. So I can create here, create like an Euler. And Euler will call DFS times from ID -1. So I don't even have to call it here. And then I will create like two RMQs here. RMQ1 is both can be integers, so like R minimum Q and like RxQ, where it would be the maximum number, right? Because this doesn't have actual Can we do this? And then RMQ can it be like, can I recreate this in a sense that now I can call in a function having A and B, and we'll return the minimum of like A and B. Is this possible? Oh, and time here, this vector. Why is this not possible? What is... Okay, I have to template. Okay, this is possible. and then RxQ is the same thing but with like a maximum here. So we have like the minimum and the maximum for some range, right? And technically I just need to call tree Euler here, and this will happen. Okay, excellent. Now that we have these RMQs inside, we can query what is the minimum time that some node from L to R is visited and what is the maximum time that some node from L to R is visited. Okay, so the query, should the query be in the QRT? I don't think so, really. Really, I think the query should be here from L to R, from like here. Okay, so let's say it like this. So the minimum is 3 dot R and Q, and then dot query from L to R. Is it inclusive though? I don't remember. I think it is, right? Yeah, it's exclusive from the one side. So this is the minimum time, and this is the maximum time. And then when we have this is only a matter of, so we have these nodes, we need to convert them to what node this time actually represents. So reverse time is reverse time at this timer is actually this node. And reverse time okay, so the reverse time is like node U is 3 dot reverse time at this and this. And now we just need the LCA between U and V, if I'm correct. So we need something. So we need some LCA between U and V, which will be a function. And then when we get the LCA between U and V, the answer is the cost at L. This should be the answer. But this function LCA, no. Is so we have to kind of pre-compute we have to pre-compute LCA, right? With like binary lifting. So yeah, let's do this. So like a jump array. Jump array here. And jump resize 2 times n-1, and all of these we'll have like the level of jump is what is enough here? So it's like log 2 of 2 times n minus 1 plus 1. It would be enough to jump it. And of course now when we calculate Euler, we want to pre-compute LCA as well. And in this thing here, we pre-compute LCA will be here in the DFS times. Why would I iterate once more? Yeah. So the parent here is this. And I will say that the LCA for, so the jump for so this is for the root node. Let me just say that this is the root node, but we know that this is the root node. So this would be resized, and now this log factor, I will get it out and I will say, okay, we have some like int log here, which would be this. I will say it like this, okay. And then the jump of the root node, I will resize it to a log. I mean, the array would have log parents, and each of these parent would be maybe plus, just to be sure, I will just do plus 2 here. And each of these parent will be root. So I don't have to pre-compute this. This is u, and now I can do here the usual LCA stuff, which is going through the root nodes from log minus 1, and saying that the jump view of L is equal to the jump of the wait, I always mess this up. This is the log factor, so this is L minus 1. Jumping upwards through L is, so jump u0 is how should we the first parent is, have I implemented it like this, or it's like parent of u? Parent of u. Parent of u is parent of u is what? Is this parent of u? Yeah, I think it is this. So the first jump is parent of u, right? And here it is where jump we're jumping u. Yeah, we constructed from the bottom one, right? Log L plus plus. So we say that the first jump is the parent, the second jump is jumping twice, is jumping from the parent minus 1, so this is like less than that and then less than that. Okay, I think that's correct. I think that's correct. Let me just check. Just check here. I think I have it somewhere. I have also, or should I have LCA? Let me check. LCA. Dynamic tree connectivity. Yeah, here is LCA, and in fact LCA is the up is this and this, yes, okay, and then we said that the parent is the 0th element. Yeah, sure, whatever. Yeah, parent is the 0th element, right? And we compute this jump here. Okay, so that we computed this jump, we will have to compute, so we have computed this, and we're just going to also I can copy this out, so I'm sure here. What am I doing here? Okay, this is, yeah, so this LCA thing here is the ancestors here. I have struct LCA somewhere. But this ancestors, I don't have timeout. That's I can build timer out. So I can build here timer out as well. Is there an easier way to compute LCA without like having time in, time out? Is there an easier way to compute? Pre-compute. Without this shit. I mean, okay, whatever, I'm not gonna waste time right now. Is ancestor. Okay, so this LCA could be inside this. Oh, hello, boy. What's up? Do you know, is there easier way to pre-compute LCA in logarithmic time without without having an Euler tour? I always do this, like have time in and time out, and then I can compute like LCA with this way here. So I can say like int LCA is this, and then I can say who is ancestor. This is if it's u an ancestor of v, so it means that the time of u is smaller or equal than the time of v, and then yeah, with binary lifting, but like you pre-compute it, right? You pre-compute binary lifting, and then like when you do this here, how do you check like if it is an ancestor of this guy? Like you do it with like how do you keep track, like with the depth or something? Also depth, yeah, depth is possible, I guess. Instead of like doing the time out here on v has to be equal than the time out of u here, and then the time out here is like time out of u is like time, let's say here like that. Now given this, we can compute this LCA. Yeah, sure, but I don't think you can link the code in the chat, so that's a kind of problem a little bit. So like LCA, computing this LCA on this tree. I think this should work. I'll check it, but also. Oh, I overwrite this. I don't think YouTube gives. I don't think YouTube allows. Oh, is this the problem? I don't think YouTube allows for. Or it could be the pre-computation problem. Is it the pre-computation problem? Yeah, problem. Yeah, links in the chat. I don't know if links are allowed. I mean, I don't know how to make it. You can send me on Discord probably. I will check it out. Let me see, did I pre-compute this correctly? Parent of view, so parent of view is, yeah, so parent of view should be fine. Oh, so you do LCA, in log square time, you mean? So because you would, for each of this step, you would check if they are ancestors in logarithmic time. So that's log squared time. Yeah, that's possible. What is the approximate difficulty of the task where you need to implement? It is probably so this technique was like in a task here mentioned in a tasking division 2 round problem E. Although if we take a look in like the latest code forces around, problem E was like, I mean, not that difficult. So where can I find the standing? So problem E was like solvable. So I solved it in what, like 30 minutes or something, and It was just like a DSU and a segment tree, some custom segment tree. But the idea is that, yeah, it's very close somewhere to here. So problem E, problem F to like division 2 round. So it means around 2000 maybe rated problems. Yeah, did you send it on Discord? Let me just check it. Let me just a moment, please. Why doesn't this pop up Discord? What's happening? Okay, I will just take a look at it. So let me just copy this so I can take a look how you implement it. So this is the code. So yeah, okay. So you go first here, okay, and then, so this is, I'm guessing, the depth of the then if they're equal, so you have found out that one of the ancestor than the other. If they're not, okay, so this is not square, this is fine, so you just pre-compute the depth here. Okay, instead of the depth you can do it this way with the timings. Most of the time I do this, but now the timings are a little bit changed because I implemented it a little bit differently here. And let me see if this crashes here for the same reason. So the jump should be on the parent of u L-1. This seems okay, right? The task, okay, so yeah, sure. Let's go over. So we're talking about this Kruskal's reconstruction tree, and in a sense of way, it's like you want to find from, like, if you're given this tree, you want to find from this node to some other node, so like from U to V, what is the maximum edge in this path. And of course this can be done with heavy light decomposition by decomposing the tree into heavy paths, and then you can query this with a segment tree. But what is this KRT is like a simpler way of doing this, and it's kind of it's much more powerful than the heavy light decomposition for some problems. So first what we do is we take the minimum edge. We take the edges we sort the edges, and then we go by the minimum, from the minimum edge to the maximum. And when we have this 3 and 6, we combine them, these two nodes. If they're not in the same component, we combine them with another node that is like an auxiliary node. This node is like a node which represents that 3 and 6 are combined with a maximum with this edge here. And you do this until you generate this KRT, which is a tree as well. So it will be a tree, and then in this tree, if you want to find in this tree what is the minimum or maximum, if you generate it like this, it would be maximum. So if you want to find what is the maximum between U and V, what you do in this tree is you find the LCA. So if I want to find the maximum between 4 and 3, you find the LCA on 4 and 3, and like for the LCA 4-3 is this node here 1-3. This node 1-3 is actually, it represents the edge here in this tree, which goes from node 1 to node 3 and has the maximum value of 10. So instead of having here, this tree will have n nodes plus n minus 1 nodes, which are auxiliary, which are like these temporary nodes. I don't know how to call them. In the way this will have two n minus 1 nodes. Yeah. So you generate this tree, and then what you can do, like you can do crazy stuff with this, especially like this problem here. Like this problem is like you have a weighted tree, and initially each nodes are deactivated, and then you can activate all nodes in some like range, or deactivate all nodes in some like range as well. And then for some node X, you want to find the maximum weight edge from X to any other activated node. And this is a little bit more complex problem, as like especially rated for division 1E problem, which is probably like 2800 level or more rated problem, but still it shows the power of this technique. And this is actual, like this is the whole code you need, like when you're merging two edges together. And the cost of the edges, so I'm building this data structure that will support each edge if it has some like cost of this edge. So you can just call this data structure and call, okay, add me an edge from U to V with this cost. And then you can add these edges with these costs in increasing order, and essentially it will just merge them into this new tree. And then I want to make this tree possible to be queryable on some nodes, so from some U to some node V. So that's why I do this function Euler, which goes through this tree and does this Euler to this tree linearization. And I have two RMQs, so like two sparse tables, that one of them is like the maximum, one of them is the minimum. So I can find, so this is like more specific to this problem here that we're solving. So this is the first problem that we're solving. Essentially, we're given some undirected graph, and we're said that we have queries of the form L to R. And these queries, you need to find the smallest integer k, such that edges from 1 to k are sufficient to connecting all of the vertices from L to R. So if I take all of these vertices from L to R, and I want them to be connected, how many of these prefixed edges do I need? So possibly this solution has like some logarithm, like some, I don't even know like other solutions to this problem. Like even like binary searching, it just doesn't make a lot of sense, like binary searching over k here. But what is the idea here is that like each edge you give some cost. You give like 1, 2, 3, 4, 5, 6 and so forth a cost. From 1 to k, from 1 to n, 1 to m or whatever. And then you build this KRT, and simply the answer is the LCA of all of these vertices from L to R. But if you try to find LCA from a set of vertices on a set of vertices, you can't easily find it, because you need to pair all of these, and it will take all of n time. But what you can do is you can have this DFS, which I showed with the timer in and timer out, so this tree linearization, and you only need to find LCA of the most left vertex and the most right vertex. So like if I have so how do I explain this? So if I have like some vertices here, so like let's say like this, and let's say like this, and I have like, okay, I will take LCA of this and this and this vertex, right? This vertex is the most left vertex and this most right vertex, and I'm sure that like the LCA on these vertices will contain this vertex as well. And how do you find this? You find the minimum vertex, you find this by saying, okay, what vertex have I visited first from this range, and the maximum vertex is what vertex have I visited last from this range. So from L to R, I need a minimum and a maximum query, which can be done with a sparse table or with a segment tree. But segment tree, of course, will be slower. I mean, I just implemented it here with the sparse table, so it would be like equivalent to like a segment tree or whatever. But yeah, I mean, and now that I have this sparse table, I have found these two vertices here. So the L and R, and now I need on the newly constructed tree, I need an LCA on them. And that's why when I iterate this tree, I want to create like the LCA. Now, one thing I have forgotten maybe is to initialize the jump here. For the root node, yeah, all of them are root, which is fine. Okay, so this should be fine, right? Like the jump from the previous node in the previous level, and I jump it like one more like that upstairs. So this should be fine, I think. I'm not really. What am I doing here? 2 0 have does it finish here? No. So this is not fine. But why is this not fine? The jump here is, well, the parent of u should be u itself, right? So u here is 2. For this technique, I don't think so. It's like pretty unknown technique. I mean, yeah, these are like two problems, or maybe more problems, but I won't recommend solving. I don't know if these actually, from my mind, here this problem is kind of, but yeah, there is these two problems here in this block, which I can post, and also there is one more problem on this technique, which actually got me interested, and it was from this round here, which is the last problem F. This is kind of something that it's kind of it generates, so they generate this, yeah, so apparently I mean, apparently, yeah, there's no actual, like, this technique is just uses a DSU and LCA, which are both in IOI term like compatible, right? And it doesn't really need anything else. So yeah, apparently, yeah, sure. So this F problem uses two such trees to solve it. So two trees, which is kind of, I mean, yeah, sure. But I had no idea. I had not even a clue how to solve this problem when the contest. Okay, I didn't have a lot of time. I had like 15 minutes to try to solve it, but still had no clue. Okay, so what's wrong here? So So U and L. What is the jump here? So what is wrong here? I mean, is it that we're maybe overflowing something? No, that should be fine here. Log of L minus 1. So I'll see what the idea here is. Jump of U, the parent. If you see any bugs here, just let me know, because I don't know what's going on. Two, yeah, 2 is the root node. 2 and then 0 and then 2 and 0. The root node has log and then the P is the parent. I mean, yeah. Oh, parent of U, yeah, parent of U should be the same here. I mean, yeah, parent of U, yeah, I see. Parent is not, a parent of U is not the same as parent, actually. Okay, this seems right. Timeout, did I? Oh, I don't initialize timeout. Oh shit. Timeout resize 2 times. This I need to initialize. Okay. Now we have some finished here things. Okay, so what is this UNV now? UNV, yeah, UNV is this here. So UNV is the okay. This seems correct, and then this seems correct. Okay, so is this correct here? Hi, Vlad. What's up? Is this correct here? I mean, I don't know which one I'm printing LCA here. That seems correct. That seems correct to me. Okay, that passed, but I'll just submit it just to see if it is correct, because I don't want to take a lot of time debugging something that is maybe correct. Or maybe some memory limit exceeded, or something like that. Oh, it's just too slow. Yeah, the suspense. Yeah, this is the suspense. Because it's my first time actually implementing such a technique, and I have no idea if it will actually pass. Why is it so slow though? Like, shouldn't be so slow. Or is it just Cold Force is slow? God, I don't get it. Okay, now it went faster. Watch it AC. Yeah, well, yeah, but it's slow. It's slow. It's like 2 seconds. So yeah, maybe because of the queries, maybe it's like a lot of queries. I could speed up the input and a lot of memory allocation as well. Yeah, that was close. That was real close, and I'm just like, what did you do for LCA? Yeah, I did my technique with the with this here with the timeout and time. Yeah, in Java would be like yeah, in Python or Java would surely be 3 minutes. But I could make it faster by unsyncing maybe here. Here unsyncing it with this, and also instead of end line, you could define end line as this end line character, so it doesn't flush all the time. Let me try it again. See how fast is that? That's faster. Okay, that's a lot faster. Okay, that's 600 milliseconds. Wow, the difference that the input makes is just insane. Insane. Wow, 600 milliseconds is insane. Yeah, 1/3 of the time. Well, it should be fast. It should be fast. I'm using RMQ instead of a segment tree, which is like off one time query. And this is like the LCA is just takes log n, but this is really fast, like really fast because it's iterative approach. So I don't see any way how to make the I mean LCA could be computed in OF1 as well, which will make it a lot faster. But it was just it's not worth it. Computing LCA in OF1 is just takes so much data structure, so much pre-processing that I don't think it's ever worth doing. But essentially, this trick of the Kruskal tree, when you have something that you want to query with the minimum and maximum on like paths, it's like always good to take a look at how you can like sort the edges first by their weight and then like construct the tree instead of doing some like heavy light decompositions. And to practice like a really simple problem, I would just maybe, if you're starting in this without much of like background, a good problem to get a practice on is something that I think it was it this problem? No. So no. A good problem was this problem actually for a good beginning problem would be to solve this one. It's quite and then you will get the idea of how and then you just learning about this this data structure would be so much easier. Yeah, so okay, so this kind of passed well. So we have this data structure. I will upload this data structure on my GitHub, so you can just take it and use it, and then you can add edges with like changing here like the cost and maybe changing here whatever you need. Change it. I think should pass for many problems. Also, yeah. Also, this I think it's too hard for us to solve now because it involves like segment tree, a custom segment tree with I don't think. I mean, it's already been 1.5 hours, this stream. It's I'm satisfied. I will just upload this code to GitHub. And what is the IOI task? I haven't read it. We could read it. So given an undirected graph, process queries of the form SE and LR, where you want to know if it's possible to reach node E from S, so from starting node to ending node, by first going through vertices of the index with indices bigger than L, so like going only with bigger than L, reaching some vertex in the range from L to R, and going vertices which are smaller than R. So it's not limited in the range, but it's limited first in like a suffix bigger than L. Then you have to reach to a vertex which is in that range, and then you have to reach the vertices which are smaller than R, so from a prefix way. It would be a sacrilegious to talk about KRT and not mention the problem that spurred the trick. So this is actually the problem that spurred the trick. So this is the original problem for the trick. This time our KRT is going to look a little different since our edges are unweighted. For processing bigger than L or smaller than R, start with an empty DSU and process the vertices in decreasing order of index. When we process a vertex, find the components of all previously processed vertex and create a new vertex of the DSU parent to all of these components. Oh, so now you don't have like two vertices that we are merging. Now we are merging all of the previous components, all of the process vertices previously. But this is probably like amortized then, like to some, like you're keeping some set probably, and then you're amortizing this, so at most n times you will merge vertices. Now for query S, the set of vertices it can reach that are bigger than L corresponds to some subtree in the KRT. So for some subtree, okay. If we build 2 for L and R, then we find the sets. Oh, see where this gets complicated? Is like it reduces to the following, that given two permutations where answer queries of checking whether it exists a common element between these two ranges. This can be formulated as a sweep line problem. We can find something stronger, the count of common elements between between the two ranges. This equals the count of common elements between so some prefix minus the count of common elements between this prefix. Okay, so the sweep on B, the process add 1 to the corresponding position binary index stream. Okay, this is kind of cool problem. Maybe we did this like as a subtask of like given two permutations, checking whether there exists a common element between these two. Yeah. So yeah, I mean, yeah, this is probably one of the hardest problems maybe it was in IOI. So day 1 problem 3. So yeah, I mean, it's not surprised, but given that it's an IOI, the subtasks are probably generous. So for like what 8 points you have some maybe possible quadratic solution here. n-1. You see this as I mean, yeah, maybe, yeah. If you see probably this some kind of problem like that, it's probably better just to solve it for subtasks for more points. But as I'm in like this is kind of cool. Like given two permutations that we can answer, we can check if there exists a common element between these two. This might be good for a basic stream later then. I mean, for today it's just it's been an hour and 40 minutes. I will upload this code right now on GitHub. So let me just okay. So this looks okay. I will just where should I put this code though? This is a very niche technique, I would say. Where should I put this code? In trees or something? Do I have trees? Do I have trees? Trees? No, I don't have trees. Maybe I should create like car, let's say car-t, Kruskal Reconstruction tree, and move this code there. So I can just add this to the GitHub repo so you guys can check it out. Okay, let me just add it here. Just add this. So Kruskal Reconstruction tree. That is definitely going into my library of algorithms. Just push here on main. Okay, so I've added it on GitHub. For those who haven't my GitHub, let me just put it here in the comments, in the chat. Yeah. So yeah, I will try to practice some more, and maybe for today it's fine. It's already been 2 hours. Thank you guys so much for watching, that you tuned in, and I see you in the next stream, right?